Hello friends, here in this video we will see what is meant by Brayton cycle and its description. So the type of cycle we are going to study here is Brayton cycle. Now Brayton cycle, the other name for it is Joule cycle. Here I'll mention that Brayton cycle is also called as Joule cycle. Next, it is also called as, the other name is constant pressure cycle. Then now this cycle, it is for a perfect gas, or we can say ideal gas.
Next,
This cycle is used as a basis for gas turbine now. Here I have written that, as the last point says, that this cycle, which is Brayton cycle, is used as a basis for gas turbine. Now gas turbine is used in case of aircraft engines and even in case of gas turbine power plants. So it means that it is used for gas turbine power plants and aircraft engines, because both gas turbine power plants and gas turbine and aircraft engines, they have gas turbine engine as their working, we can say, power plant which produces the power. So that power producing device works on the constant pressure cycle called as the Brayton cycle. Now we'll even understand why it is called as constant pressure cycle. So when I'm starting with Brayton cycle, first I'll draw a simple diagram of a gas turbine power plant, and on that I will be explaining the Brayton cycle. So here I am drawing a layout of simple open cycle gas turbine. Here I am drawing the diagram of a simple open cycle gas turbine. Now, here if we see, we are having the devices. I have written C here and here it is T. Next, here I am writing CC. Then this will be the fuel which is sprayed, mass flow rate is m dot f. Here I'll say that where C is called as compressor, T is called as turbine, and here I'll call it as G. This G is called as the generator. Now, how this cycle works is, first of all, when the compressor starts rotating, there is atmospheric air which is coming inside the compressor. That atmospheric air is input to the compressor, and as we see, when the air moves over the compressor, the volume of the air will go on decreasing, as can be seen from this diagram, and finally that same air goes out. So here I am having compressed air, out. So here, during the compression process, the pressure of the air will go on increasing and volume will go on decreasing. It means there will be rise in pressure, rise in temperature, but volume will go on decreasing. So atmospheric air is in. I will call this as state number 1, and when the air is getting compressed, the state changes, so this will be state 2. Now this high pressure air which is compressed goes into CC, which is called as combustion chamber. So when this high pressure air it enters the combustion chamber, fuel is sprayed inside the combustion chamber, and then air and fuel mixes. Because of that there is combustion produced, that is the fuel starts burning, and after the combustion chamber we are getting gas, which is a mixture of air and fuel. Now this gas is having even high pressure and temperature which was there in compressed air, which was out of the compressor. So at this state, I'll call it as state 3. Here the pressure and temperature is even higher as compared to the state 2 when it was only compressed air. So when the fuel gets sprayed, the pressure and temperature further increases and we reach state 3. And now these gases, they are input to this turbine at, we can say, volume V3. During the passage through the turbine, the volume of gas will go on increasing, and at the same time temperature and pressure will drop, and we will get the work output, that is the rotation of turbine. And finally the exhaust gases, after doing the work, the exhaust gases are thrown out of the turbine. So when we get the rotation of the turbine and compressor, they are connected on the common shaft. So when turbine starts rotating, it even rotates the compressor. It means in order to drive the compressor, the power is given by the turbine itself. And if we see onto the other side of the turbine, there is a generator. It means the work output which we are getting in the form of rotation of shaft can be fed to the generator, and then in that generator the mechanical work will be converted into electrical energy. So then it would be called as a gas turbine power plant which develops the energy. And if we don't have the generator, then this much unit which would be used in case of aircraft engines. So we have seen here what is the layout of open cycle gas turbine, and now the Brayton cycle I will explain considering this open cycle gas turbine. So now here I am going to explain the Brayton cycle based on this open cycle gas turbine, in which when the gases are exhausted we are having state 4. So these points 1, 2, 3 and 4 I'll show it on Brayton cycle. Next, PV and TS diagram for Brayton cycle. Now, first I'll write the processes which are there in case of Brayton cycle. The processes that take place in Brayton cycle are: first, process 1 to 2. As we can see from the simple open cycle gas turbine, from 1 to 2 the process is compression. At point 1 the atmospheric air enters the compressor, it then gets compressed, that is volume decreases, pressure increases, it goes up to point 2. So from 1 to 2 I can say that the compression is reversible, adiabatic or isentropic compression. Next, process 2 to 3, it is at point 2 the compressed air enters the combustion chamber CC where the fuel is sprayed, and from 2 to 3 we can say that it represents the heat addition process because fuel was added. So 2 to 3 is called as constant pressure heat addition, because in case of Brayton cycle we are adding heat at constant pressure. Next, process 3 to 4 is again reversible, adiabatic or isentropic expansion, because as we see here from 3 to 4 there is expansion in turbine, so that expansion is taken as reversible adiabatic or isentropic expansion. Next, process 4 to 1 is constant pressure heat rejection. So after this, that is once we have got the expansion process, next 4 to 1 will represent a constant pressure heat rejection. Now these processes I'll show it on PV and TS diagram. So the first one is reversible adiabatic or isentropic compression. So from 1 to 2 it is reversible adiabatic or isentropic compression. As we see, the volume at point 1 is more, volume at point 2 is less, so during compression the volume decreases and pressure increases from P1 to P2. Next, 2 to 3 is the constant pressure heat addition process, so heat will go on adding from 2 to 3, keeping the pressure constant. So pressure at point 2 and 3 both are same, P2 is equal to P3. Next, process 3 to 4 is reversible adiabatic or isentropic expansion. So like compression, even expansion will be a curve on PV diagram. So 3 to 4 represents the expansion process, and as we see, before expansion the volume is V3, after expansion the volume is V4. Then from 4 to 1 it is constant pressure heat rejection, so again the pressure is kept constant from 4 to 1 and then the heat is getting rejected. So this is the Brayton cycle on PV diagram. Here process 1 to 2 and process 3 to 4, they follow the same law, which is PV raised to gamma is equal to constant. Next, heat is added during process 2 to 3, so heat addition. Heat is rejected from 4 to 1, so heat rejection. As we can see here, from 2 to 3 the heat is added in the combustion chamber, from 4 to 1 the heat is rejected to the atmosphere. So we have shown heat added, heat rejection. During 1 to 2, as we see here, the device is compressor, so 1 to 2 indicates the work done in compression, so work is input to the system. And then from 3 to 4 we can see that we are getting the work output in turbine, so that is the work we are getting in expansion, so it is W suffix E. Now on Brayton cycle, the Brayton cycle I'll show it on TS diagram. So here the first process is isentropic compression, so it will be shown on TS diagram with the help of a vertical line. That is, the compression process is from 1 to 2 and here the entropy is constant, that is S1 is equal to S2, and temperature rises from T1 to T2. Then from 2 to 3 it was constant pressure heat addition, so here I'll draw a constant pressure line, P is equal to constant, and heat is added keeping the pressure constant. It means we have to follow this line having constant pressure. So 2 to 3 indicates the heat addition process, and here the temperature of point 3 is T3. So from 2 to 3 it is constant pressure heat addition. The pressure of point 2 and point 3 both are same as it is constant. Next, from 3 to 4 it is constant entropy expansion process, that is isentropic expansion. From point 3 to 4 the entropy remains constant, that is S3 is equal to S4, and the temperature drops from T3 to T4. Then at last we have constant pressure heat rejection. So again I'll draw a constant pressure line connecting point 1 and 4. So this is the constant pressure line. Heat is rejected from 4 to 1. So here is the heat rejection from T4 to T1. Here during 2 to 3 the heat is being added, so this is heat addition. During 4 to 1 heat is rejected, so that is heat rejection. Next, during 1 to 2 the work was input to the compressor because we require work to drive the compressor. From 3 to 4 we are getting the work output which is there in case of turbine, so work we are getting in expansion. So here is the PV and TS diagram for Brayton cycle. So now here I have drawn the PV and TS diagram for Brayton cycle. Next, as we have seen in Brayton cycle, the heat addition was at constant pressure, heat rejection is also at constant pressure, so it is also called as a constant pressure cycle. Then after this I'll write down the formula of efficiency. Since thermal efficiency for Brayton cycle is given by the efficiency of Brayton cycle is equal to heat added minus heat rejected upon heat added. So therefore the efficiency of Brayton cycle will be equal to heat added is Q suffix A minus heat rejected is Q suffix R upon heat added. Now therefore the efficiency of Brayton cycle will be equal to QA upon QA, that will give me 1, minus QR upon QA So this is the formula from which the efficiency of Brayton cycle can be calculated. I'll write down what is QR and QA. So first of all, therefore heat added at constant pressure is given by QA या Q suffix A is equal to MCP heat is being added from 2 to 3, so the temperature difference is T3 minus T2, so MCP T3 minus T2 and then heat rejected at constant pressure is given by Q suffix R is equal to MCP. Heat is rejected from 4 to 1, that is T4 minus T1. So this is the formula of heat rejected, and since the heat added, heat rejected both are at constant pressure, Brayton cycle is also called as constant pressure cycle. And once we know heat added, heat rejected, we can put their values in this formula of efficiency of Brayton cycle and get the answer for efficiency of Brayton cycle.